This is lesson 4.8 on logarithmic equations. So in this section, we're going to encounter two different types of equations involving logarithms. We're going to actually talk about the type of equation that we're going to see in our application problem first. It seems simpler, but actually requires a little bit more work than what we're going to see for the drill problems. From what we remember with our logarithmic functions, we introduced them as the inverse functions of our exponential functions. Now remember, only one-to-one functions have inverses, so that means that our logarithmic functions are one-to-one. So if you recall, with our exponential equations, we said that when we got to the point where we got exponential function equals an exponential function, where those two functions have the same base, we were able to drop the base and just equate the exponents. We said the reason we were able to do that is because exponential functions are one-to-one. Since logarithmic functions are one-to-one, we have a similar trick up our sleeves. If we ever have log base a, say, of something equals log base a of something else, since logarithmic functions are one-to-one, we can drop the logs and simply equate the insides of those two logarithms with each other. Now that seems simple enough, but we are making a few assumptions behind the scenes when we do that. Mainly, we're assuming that there is a way that those two things can be equal. If we think about it in terms of graphing, we assume that there is a way that we can find where those two things intersect. That's not always going to be the case. So it very well could be likely that we have two logarithmic functions that do not intersect. So what we need to do with our logarithms is once we go through this process, once we drop the logs and solve where the insides are equal, we need to check that they are actually solutions to the original equation. So that takes a little bit more work, and we're going to see that with our application problem. For our drill problems, what we're going to do is use a very useful and very important fact. Whenever we have a logarithmic equation, so especially when we have a logarithmic equation of the form logarithm of something equals a constant, there is going to be a corresponding exponential equation. So for example, log base a of b equals c, that logarithmic equation is saying the exact same information as the exponential equation a to the c equals b. So log base a of b, that is saying, all right, a to the c equals b. I'm asking myself, a to what power equals b? Well, it's a to the c equals b. Guess what? That's exactly what I'm saying in my exponential equation. So for every logarithmic equation, there's a corresponding exponential equation, and vice versa. For every exponential equation, there's a logarithmic equation. We're going to use that fact a few different times in the remainder of this chapter. So be mindful of that. This is exactly what we'll be using for the drill problems for this section, and we're going to be using that fact later on in this unit as well. So let's consider this example. So log base 4 of 3x minus 5 equals 3. So notice that our variable is stuck inside a logarithm. That's generally going to be bad news. So we don't want to keep the log in this equation because there's really no easy way to get the variable outside of the logarithm. So what we're going to do is we're going to write the corresponding exponential equation. Remember, we just said that for every logarithmic equation, there's a corresponding exponential equation. So what we're going to do is we're going to look at the base of the logarithm. So here it's base 4. That is going to be the same base of our exponential function. So we're going to have 4 to some power. The power is going to be what's on the equal sign over here, what's on the other side of the equation. So we're going to have 4 to the third power equals, now what was formerly inside the logarithm is going to have its own side of the equation. So this kind of flip-flops. The base stays the base, and what was trapped inside the logarithm is now free, and then what was free before is now trapped inside the exponent. So this works both ways. There are some times where we're going to have something like this, similar to this, that we will rewrite as this to help us solve an equation. But in this time, we're going in this direction. We're starting with a logarithm. We're wanting to rewrite it as an exponential equation. So the base of the logarithm is the base of the exponent. This number here becomes the exponent, and then what was inside the logarithm gets its own side of the equation. So from this point, for our drill problems, it's just going to be a simple linear equation from this point. This is the hardest step right here. So if you do this correctly, you're golden. All right, 4 cubed. 4 times 4 is 16. 16 times 4 is going to be 64. So 64 equals 3x minus 5. Add 5 to both sides, we get 69 equals 3x. Divide both sides by 3, I get 23 equals x. And there's my final answer. So just remember, when we have a logarithmic equation, there's a corresponding exponential equation. Rewrite the logarithmic equation as an exponential equation. Go ahead and simplify the exponent here. And then for the drill problems, once again, it's just a linear equation at this point. Simplest thing in the world, well, all right, maybe not the simplest thing in the world, but it's by far and away the simplest thing that we've encountered in this class. So I hope that we could do this in our sleep by this point. All right, here's another one. So we've got a logarithmic equation. Our variable is trapped inside the log, so the very first thing we're going to do is rewrite this as an exponential equation. So the base of the logarithm becomes the base of the exponential function, and then this number here is what becomes the exponent itself. And then what was inside the log is free on the other side of the equation. All right, x to the 1/3 power, remember that's the same as taking the cube root. So x to the cube root, the cube root of 8, that's going to be 2. So 2 equals 3 minus 2x, subtract 3 from both sides. Get -1 equals -2x, divide by -2, and we get x equals 1/2. Now a common thing that I've seen before on these is, let's make up something real quick. 3 minus 2x equals 1/2. I'm not going to go through this whole problem. So very similar to what we have here, but we have log base 4 of 3 minus 2x equals 1/2. So we're going to rewrite this as 4 to the 1/2 power equals 3 minus 2x. Now 4 to the 1/2 power, that's going to be the square root. Now, I've seen students do this before. They're going to say, all right, I'm taking the square root of this, so I need to make sure I don't forget my plus or minus. Actually, we do need to forget our plus or minus. We're not going to do that here. Do not put in that plus or minus. The only time that we need to put in an extra plus or minus when we are taking the square root is if we are given an equation and we take the square root of both sides. So here, if you need to take the square root of the base, just take the square root. Do not make it negative. So just leave it as positive 4 to the 1/2. So don't overthink it. This is one of those, we've seen many examples of where you can make a stupid mistake. This is where you can make a smart mistake. You think you're being very good in remembering to put in the plus or minus, but don't do it. That plus or minus is not needed here. You only put in the extra plus or minus when you're given an equation and you actually take the square root of both sides. We are not doing that here, so don't worry about it. All right, so let's consider the problem that's going to lull us into a false sense of security. So solve log base 4 of 4x plus 7 equals log base 4 of 2x plus 1. Now, usually these would not be that difficult unless things just go wrong. And unfortunately, in this case, things just go wrong. So what we need to do, we have a log equals a log. They have the same base. So we said that since logarithms are one-to-one functions, we can just drop the logs. So where is this going to be true? It's going to be true when the insides are equal. So when 4x plus 7 equals 2x plus 1. So this is a nice, simple linear equation. Let's subtract 2x from both sides. So 2x plus 7 equals 1. Subtract 7 from both sides. So 2x equals -6. So x equals -3. All right, so no big deal. Seems like x equals -3 is going to be our answer. But if we go back and try to plug this back into our equation, we have log base 4 of 4 times negative 3 plus 7 equals log base 4 of 2 times negative 3 plus 1. So that gives us log base 4 of, let's see, that'll be negative 12 plus 1, so that's going to be negative 5, equals log base 4 of, let's see here, negative 6 plus 1, so negative 5. So we get the same thing back, so it works. Well, not entirely. Log base 4 of negative 5. So if we think about this on its own, I hope that this makes us sad. We're asking here 4 to what power equals negative 5? Well, you can sit and think about it for a little bit and think about it for a little bit longer, and you're not going to figure it out. There is no number that when we raise 4 to that power, we get negative 5 back. There's just no way that we can put an exponent here that's going to give us a negative number back. And when we think about it a little bit more, this makes sense because recall the domain of our logarithmic functions is x has to be bigger than 0. So what's inside the logarithm must be positive. Here it's negative, so this makes no sense. So the only way that this could be equal is if we could take the log of a negative number, but we can't. So in this case, there's just simply no solution. Now the only way we could know for sure that there's no solution is by going through this work. All right, so now what went wrong? So why is there actually nowhere where these two things are equal? We said that when we have a log equals a log that we can just drop the bases. And that makes, or drop the logs because they're one-to-one functions. So why did things go awry? Well, the reason is going from here to here, we made a logical but nonetheless a false assumption. And that assumption was there is somewhere where these two things are equal. So if there were a way for these two to be equal, it's going to be exactly where these two things are equal. But our assumption was wrong. There is nowhere where these are equal, and that's why we got a bad conclusion here. So in general, when we're working with logarithmic equations, it's always a good idea to check your answer. Now for our drill problems, I've gone through and made sure that we're not going to run into weird things like this. And for the types of problems that we're going to see from this section, we can't go wrong. There's not going to be any way that we will miss this, that we won't have a solution. But when we're dealing with critters like this, there are times where they miss each other, and so there are times where there's just no solution. So always double check your answers. Make sure that what you found is in fact going to work.